So now we want to find the volume of y equals sine x when we revolve it about the x-axis on the interval from 0 to pi. So remember the basic sine graph. Looks like this. Okay, it comes up and then hits down at pi. And gets to its highest point up here at 1. Starts at 0, and at pi it's back to 0. Okay, so that's the basic function, y equals sine x. And then, once again, we look for our radius. Let's see. Again, it's just going to be the function itself. And on the x-axis here, we'd be going between 0 and pi. Okay. So what we have here is the integral from 0 to pi of pi times the sine squared of x dx. Okay. Or, if you want, the integral pi times the integral from 0 to pi of the sine of x squared dx. But whichever way we write it, we've got a problem here. We've got a problem that we hadn't encountered in some of our other examples. And that is, I can't do substitution here to take care of that. Because if I tried to let u be sine x, then du would call for a cosine x. I don't have a cosine x in here. Right? No cosine hanging around here to absorb, to do that substitution. So what we have to do here is we have to bring in some old trig formulas that you probably weren't asked to memorize, because in trig there wasn't a whole lot of point to them. But when we're dealing with either sine squared or cosine squared, and we're going to see more of this later when we deal with some integrals with our trig functions, we need these two identities. For cosine squared, we can rewrite cosine squared as 1 plus cosine of 2x over 2. And for sine squared, we can rewrite that as 1 minus cosine of 2x all over 2. And that's actually the key in this problem, is we're going to take the sine squared here and rewrite it as 1 minus cosine of 2x over 2. And that's really the only tool we have to be able to do that. So when I plug this in, I'm going to go ahead and factor the 1/2 in the bottom out, put it with the pi out front. So I have pi over 2, integral 0 to pi of 1 minus cosine 2x dx. And see, the advantage of this identity is that I can do the integral. I can do the integral of cosine 2x by substitution, whereas I can't do the integral of sine squared by substitution. So this is actually going to be two separate integrals, so let me just go ahead and break it apart. I'm going to have pi over 2 integral from 0 to pi of 1 dx minus pi over 2 times the integral from 0 to pi of cosine 2x dx. So cosine 2x is a composite function. So I'm going to do the substitution here. U equals 2x. Du calls for a 2 dx. So I need 2 to go in there with the dx to carry the substitution through. So I can put the 2 there, but then I have to divide by it on the outside. So this second part will actually look like this. Pi over 4 integral 0 to pi of cosine 2x 2 dx. So now this integral is set up for its substitution step. So we can carry that through. It's integral cosine u. Integral cosine is sine. And this one here we can, of course, also go ahead and carry through. So this will be pi over 2x minus pi over 4 times the sine of 2x, and then all of that is evaluated between 0 and pi. Okay. And then we just go through and compute this. So plug in pi. That's going to be pi over 2 times pi minus pi over 4 times sine of twice pi. Sine of 2 pi is still just 0. And then minus, plug in 0, pi over 2 times 0 is 0. Sine of 0 is 0 as well. So it turns out the volume beneath the sine is actually pi squared over 2. The volume beneath the sine is pi squared over 2.